In this session, we will be going through the concept of space-time diversity and the diversity technique called Alamouti block code. It is a complex space-time diversity technique that can be used in MESO mode or in MIMO mode. Compared to a conventional single antenna system, the channel capacity of a multiple antenna system can be increased without using additional transmission power or spectral bandwidth. Due to the ever increasing demand of faster data transmission speeds in recent or future telecommunication systems, multiple antenna systems have been actively investigated and successfully deployed in the emerging broadband wireless access networks. For example, mobile WiMAX, etc. MIMO techniques. MIMO technologies can be divided into two main categories: diversity and spatial multiplexing. The diversity techniques intend to receive the same information bearing signals in multiple antennas or to transmit them from multiple antennas, thereby improving the transmission reliability. In the spatial multiplexing techniques, on the other hand, the multiple independent data streams are simultaneously transmitted by the multiple transmission antennas, thereby achieving a higher transmission speed. Types of diversity. The types of diversity based on various ways of realizing diversity gain are: spatial diversity. Sufficiently separated multiple antennas are used to implement independent wireless channels. Polarization diversity. Independent channels are implemented using the fact that vertically and horizontally polarized paths are independent. Time diversity. The same information is repeatedly transmitted at sufficiently separated time instances. Frequency diversity. The same information is repeatedly transmitted at sufficiently separated frequency bands. Angle diversity. Multiple receiver antennas with different directivity are used to receive the same information bearing signal at different angles. 3D representation of various diversity techniques. In the figure below, we can see that time, frequency, and spatial diversity techniques are illustrated. In time diversity, data is transmitted over multiple time slots. In frequency diversity, the same data is transmitted at multiple spectral bands to achieve diversity gain. In spatial diversity, data is transmitted using multiple antennas. Now that we have seen the various diversity techniques, we will proceed with Alamouti block code. The diversity technique Alamouti block code is a complex space-time diversity technique that can be used in a 2-into-1 multiple input single output mode or in a 2x2 multiple input multiple output mode. The Alamouti block code is the only complex block code that has a data rate of 1 while achieving maximum diversity gain. In this slide, we can see the 3D representation of Alamouti block code. As we can see in the figure, there are two time slots each in two different spaces operating on a single frequency. We can also see that the contents of time slot 2 are conjugates of the data held in adjacent space time slot 1. Hence proving the statement Alamouti block code is a complex space-time diversity technique. Briefly, two antennas are used to send two OFDM symbols and their conjugate in two time slots, which brings a diversity gain without having to compromise on the data rate. Over the air, the transmitted symbols will suffer from channel fading, and at the receiver, their sum will be received. Here is the schematic diagram of an Alamouti wireless system in 2x2 multiple input multiple output mode. Let's consider encoding and decoding of a wireless Alamouti system with two transmitters and receivers. Since the transmission is done over two periods of time, the decoding will also be done over two periods of time. At the receiver, the received vector y can be represented by the following equations. In the equations seen here, subscript number denotes the antenna used for receiving or transmitting, and the superscript number denotes the time slot. Here, Y represents the received OFDM symbol, X represents the transmitted symbol, H represents the channel coefficient, and N represents noise. Here, H12 is the channel coefficient for data from transmitter 1 to receiver 2, which can be clearly seen in the previous slide. We can see that in time slot 1 received OFDM symbol depends on X, and in time slot 2 received OFDM symbol depends on X conjugate. To obtain the symbols back from the receiver side, both the equations from the previous slide can be combined easily and arranged to produce the result as shown. The next step is to find a way to isolate the transmitted symbols x1 and x2. One way to reduce the number of unknowns is by using a channel estimator to estimate the channel coefficients. Let's assume in our OFDM reference design, channel estimation OFDM symbols are sent with each transmitted packet to enable estimating those channel coefficients at the receiver. Given the following matrix of H, we can isolate x1, x2 by simply multiplying the matrix Y by the inverse of H. However, since this matrix is not square, we need to use the Moore-Penrose pseudo-inverse H plus to solve our equations. Using the inverse matrix expression obtained in the previous slide, the noisy estimated transmitted symbols can be found using the following expression. The last step would be to make a final decision on the transmitted symbols. In our OFDM reference design, the decision is made based on the minimum squared Euclidean distance criterion. In this figure, we can see that the addition of diversity to the system brings a significant performance gain in terms of bit error rate in simulation. For the same EB over NO value, we can see that Alamouti block code gives the least bit error rate. Concluding the session on Alamouti technique, we can say that the Alamouti space-time block coding is a simple MIMO technique that can be used to reduce the BER of a system at a specific SNR without any loss on the data rate. The presented decoding technique is called hard decision based zero forcing and is probably the simplest to implement in hardware. It is a linear decoding technique that has a low complexity. That being said, further reductions in BER can be achieved by using non-linear decoding techniques, which are usually better than linear techniques, and also by using soft decision techniques with specific QAM constellation decision boundaries.